that. But this is a 20th century scientist who worked in Uppsala in Sweden and got a Nobel Prize in 1926 or 27, I forget now, 26 I think. And anyone know what this is? You know these 30S ribosomes, 70S ribosomes, and for the food people, the 11S C globulin in soybean. What does the S stand for? S stands for? The big S. Come on, the food scientists, nutritionists should know this. You've heard of C globulins and 11S, 7S proteins, all this. What does the S stand for? Oh, okay, the biochemists and ABTs, they'll know this because they do DNA, ribosomes and things. What does the S stand for? Yeah. You're just teasing me, aren't you? Really? What's this? Whiteboard. Okay, so the 11S soybean globulin, S stands for. What's the unit of sedimentation? S. The Svedberg unit. Svedberg. So who's this? Svedberg, yes. Okay, this is Theodor Svedberg. And when we have a little tour later, I'll show you Svedberg's logarithmic tables that we've got in our possession now, with a nice little message in Swedish. In fact, did I show you when the Abbey and ABTs, when I took you a little tour around the labs, did I show you the log tables? No? Okay. That delight is to come. Right, that's Svedberg. We've got the Nobel Prize for in 1927, there we are, for the invention of the analytical ultracentrifuge, a technique which, like a lot of techniques, which revolutionized biomolecular science, and it was using this method that proved once and for all that proteins were discrete molecular entities. They were large molecules rather than another theory about them. They were just a colloidal mass, really, without any real form. So it was the ultracentrifuge, which was invented by Svedberg in the 1920s, which sorted that out, and which is why he got his Nobel Prize. And this is what an ultracentrifuge used to look like. I first visited the Svedberg laboratory in, when was it? I was invited to give those lectures. 1990, I was invited over to give a lecture in Uppsala, and I went in to look for this instrument inside the room, the Svedberg centrifuge, and all it was that the room. It was a room full of pipe work and equipment and things, and it wasn't a noticeable box or or instrument. It was just a room full of bits and bobs. Like this is a photographic plate here. This is a Pirani gauge for measuring pressure, because we spin things at very, very high speed, so it has to be at a very high vacuum. And there's a refrigeration to control the temperature and everything. So it wasn't an instrument as such. It was just a room full of pieces of optical equipment, of vacuum pumps, diffusion pumps, refrigeration devices and things. It was the whole room was the ultracentrifuge. So part of the Svedberg analytical ultracentrifuge. Actually, we can reduce this a little bit. If we go No, can't do that.
Control minus.
Control
Right upper corner.
minus, here we are.
No, the other end.
That's it. That's the one, okay? Fine. Is that still readable?
Yes.
Yeah. Okay, let's have the... What's he doing? No, unless you don't know why all the curtains are drawn, but let's proceed with this. So this lecture is about the sedimentation analysis of macromolecules, deriving from this wonderful instrument that Sedberg invented in the 1920s. So a centrifuge is simply a device for spinning things, for separating particles out. I think everybody here has used a centrifuge at some stage in your practical careers for clearing debris, cell debris out, or purifying a food solution from particulates and things. Who hasn't used a benchtop centrifuge before? Well, okay, we'll make sure that that is rectified. So it's a way of increasing the G-force. We're all familiar with stuff with sediments under gravity, but at very high speed we can sediment small particles by increasing the G-force. So the higher the rotation speed, the higher the G-force. And you need very high sedimentation rotation speeds in order to sediment very small particles, that is, macromolecules, proteins, nucleic acids, and carbohydrates, polysaccharides. So that's why we use an ultracentrifuge. Ultra means very high speed. And in preparative centrifuges, these can go up to 75,000 RPM. That's extremely fast. An analytical centrifuge is a specially adapted centrifuge where during the sedimentation process, as particles, molecules are sedimenting, by use of a special optical system, we can actually follow the sedimentation process. Okay, we can see how fast things sediment. Obviously, it depends on the speed. The higher the speed, the faster they will sediment. But for a given rotor speed and the given conditions of temperature, solvent and things, then the rate at which a particle will sediment depends on its size and shape. Because bigger particles tend to sediment faster under these G-forces. And conversely, the more asymmetric a particle is, the more friction it experiences as it sediments, and therefore the slower it will sediment. So the sedimentation rate, as measured by these Sedberg units, depends on how big the particles are, how big your proteins, your nucleic acids, or whatever they are, and also how extended the particles are. Generally, larger particles sediment faster and compact particles sediment faster. So this sedimentation method is a wonderful way for assessing the sizes of particles and also the conformations, especially when used in conjunction with other techniques like electrophoresis, as we'll see later when we show an example. And there are two types of sedimentation method. Actually, let's have a bit of light in here. Let's have some real light rather than artificial light. Ooh. Better. So there's two types of sedimentation technique. This disco effect outside, I think we've seen that one before, haven't we? It's gone and fixed it. Right. There's two types of sedimentation technique. One is sedimentation velocity, where we spin things at very high speed and particles will sediment, as I just described, depending on their sizes and shape. And following the progress with our optical system, we can get the sedimentation coefficient, symbol little s, whose unit is the Svedberg unit, which is big S. There you go, little s and big S. Sedimentation coefficient, and we'll define that in a minute. S, which is a measure of the size and shape of a macromolecule. But there's another technique we use, using the same instrumentation, and that's called sedimentation equilibrium. And what happens under equilibrium sedimentation is, instead of spinning things at very high speed, in fact with an analytical centrifuge, generally they go up to only 60,000 RPM because of the windows that we need for the optics things. We can't go to the same high speeds that a preparative centrifuge will go to. Preparative centrifuges are used to separate materials for purification purposes. Analytical centrifuges are used to analyze the particles that are sedimenting to get information about their sizes and shapes. Okay? Preparative centrifugation, the separation and purification of materials. Analytical centrifugation for analyzing their sizes and shapes. So we use different, and we'll show you when we have the demonstrations, different types of containers for running preparative centrifuges using plastic tubes. And for analytical centrifuges, we use these special, expensive metal containers with windows, quartz or sapphire-based windows, so we can shine light or UV radiation through to do the analysis. And because of those, we can only run at a maximum of 60,000 revolutions per minute. That's okay. So that's velocity sedimentation, very high speeds, up to 60,000 RPM, looking at the sedimentation rate. But if we run our centrifuge at lower speeds, so instead of 60,000 RPM, we ran our favorite protein solution, which is ovalbumin. That's right. If ovalbumin solution was being run, say, at 20,000 RPM, then what happens is, as we sediment macromolecules in a container, okay, so the force is spin like that, and there's a force outwards. So the macromolecules will tend to pile down to one end of the container, leaving clear liquid behind. But that, in a way, is against the second law of thermodynamics, which likes to make things all random. So pushing all the protein or carbohydrate or the nucleic acids down to one end of the cell, there's a force which opposes that. What's the force which has to push everything back and spread everything out nice and even? diffusive forces, yeah. Diffusion tries to spread everything out. So you've got sedimentation that way, and diffusion trying to push everything back. Now, at very high speeds, sedimentation wins, okay? The forces are so great that the diffusion forces backwards don't push the molecules back. But at lower speeds, say at 20,000 RPM instead of 50,000 RPM, these forces become matched. So you have sedimentation forces that way being balanced by diffusion forces pushing the molecules, trying to spread everything out. And after a period of time, it could be 24 hours or so, these forces come to equilibrium, and we have what's called sedimentation equilibrium. And what happens is you get, instead of a sedimentation boundary, you get a distribution of material which stays constant with time. So the two forces sort themselves out, sedimentation, diffusion, and you end up with a steady state. That means constant distribution of material. And because there's no movement in this steady state, then friction forces and things don't apply. So the distribution depends only on the molecular size of the macromolecules and not on the shapes. So no friction, shape effects disappear. So whereas this technique here depends on the size and shape, this technique depends only on the size. So this gives the molecular weight directly. And then if we know the molecular weight, we can go back to the sedimentation coefficient and work out the shape of the molecule. So using the same instrumentation, an analytical ultracentrifuge, and using sedimentation velocity and sedimentation equilibrium, we can get the size, the molecular weight, and then we can get also the shape or conformation of the molecule. So it's a very, very powerful method, which works beautifully in conjunction with electrophoresis, as I'll show you in a minute. Right, so that's the old centrifuge, which is a room full of components, optical components, refrigeration, vacuum, this sort of stuff. Why do we need a vacuum, by the way? Why is the experiment run in a vacuum?
Yeah, the air heats up.
Yeah, so what would happen at these speeds?
Well,
Get very hot. Yeah. That's right. So you put your sample in for analysis and you have no sample left. Probably no centrifuge left either. You didn't have a vacuum. So you have to run in a vacuum because of air friction. And so that's why we use high vacuum conditions. It's not necessary for low-speed benchtop centrifuges. Vacuums are not necessary, but for very high speeds is necessary. This is a modern instrument. This is the same modern. We got this in 1990. We still regard it as probably before you guys were born, 1990, well before you guys were born. That's what it looks like now. Rather disappointing. In fact, it looks rather like a washing machine, that's right, with spin-dry facility. But you wouldn't want to put your clothes in here. Definitely not. Because you have no clothes left, and also you have no centrifuge left if you put your clothes in one of those. But it does look like a washing machine in many ways. So you put your sample in what's called special rotor. In fact, you probably see this better here. If you take the front of the instrument, then you'll see something like this. So you've got the rotor, which contains these tubes or cells. If it's a preparative centrifuge, you'd use a plastic tube. If it's an analytical centrifuge, you'd use precision cylindrical types of cells with transparent windows. And with the analytical centrifuge, you have a light source which shines light through the solution, which is inside this, what we call cell. And then, because it's spinning very fast, but every time it gets to, a cell gets to here, in the orbit, the light passes through. The rotor has to be balanced so that you have to have an equal weight cell on the other side of the rotor. Otherwise you get an imbalance and an accident. But all modern instrumentation now has a check to see if your rotor is balanced before you switch on. So if you have made an error in terms of forgetting to put a balance cell in or whatever, the centrifuge won't work. So light is passed at the appropriate wavelength. If it's a protein, we would use what wavelength? 280, yeah, nanometers, yeah. Or we could use a different type of optics, not absorption optics. We could use something called refractive index optics. Remember that? If we're looking at a polysaccharide solution. Okay, so you've got that choice of optics, UV absorption or absorption optics or refractive index optics. Oh, that's good. You've done all that. Yeah, that's, so we look at it, we see how it all fits in now, all these optical systems and things. And this is built into the centrifuge. You've got the choice between UV or refractive index optics, which we can also use for proteins as well, by the way. You don't have just to use ultraviolet optics for proteins. You can use refractive index optics, as you can do for any macromolecule. Okay, so the light goes through the cell when it gets to this part of the orbit, and then it scans across the cell, the sedimentation process, and then the signal gets picked up or gets sent through this slit lens arrangement to a detector. So if it's absorption optics, it'll be some sort of photomultiplier. If it's refractive index optics, it's some sort of CCD camera which detects the pattern, and the information is then sent through to a computer for analysis. So that's what's going on inside here. Obviously it's more complicated than that. I haven't shown all the refrigeration vacuum devices and things and the optics, but that's the basic principle, and the data goes to the computer. And looking at this curve here, this looks like a steady state sedimentation equilibrium experiment. So the operator is wanting to measure molecular weight. Yeah, absolutely. Yeah. You can see from the age of this computer here, this photograph was taken a long time ago. And actually, we got the very first instrument, as you'll see. We got the very first one. This was made in 1990 by Beckman Instruments in 1989. We got the very first instrument, serial number 1. There's now over 1,000 of these worldwide, largely in biopharma and some food companies for analysis, also in academic laboratories. But we got the first ever Optima centrifuge. There were instruments before that. They looked like battleships, really. We had 3 older instruments before we got the Optimus, but now we have three of these. So we've got 3 of these in our laboratory. And when we had the old instruments, people used to call us the Nottingham Science Museum, which was a bit unfortunate because we got all these old centrifuges thrown out by everybody else. And then they were replaced by 3 of these XLAs. So we transferred from being the Nottingham Science Museum to the Nottingham... No, what you get... No, not quite. Oh, that's what you did actually. Okay. So what you call a room with lots of washing machines in. A laundress, that's right. So we became the Nottingham laundress. Aren't they cruel fellow scientists? Yeah, this was before your time, Glenn. Horrible. Science museum to that. Yeah. In the older instruments, we used to have to cool them with external water supply. So I do waffle on, don't I, with anecdotes. And these equilibrium experiments can take a long time. They can take 2 or 3 days to get to equilibrium. So I had run one run on overnight, and I was on my way to Cambridge to see my old boss. So I thought I'd nip in, check everything was okay. Open the door, and this tsunami of water came out of the lab. What happened was, and it shows you how well sealed the doors were in those days, is that the pipe had blown off the back of the centrifuge with the water pressure. And overnight the water just accumulated. There's no drain in the lab, so it opened the door. This tsunami of water came out straight into the head of the department's office, who was next door. Over all his carpet. It wasn't a good idea. These sort of things don't happen anymore because you've got all these little checks and things on instrumentation. It's not. I wouldn't say it was exciting when things like that happened. And also with an older instrument, the drive spindle which holds this rotor on snapped, and I was downstairs in this building which doesn't exist anymore. It's actually where the barn building is now. That used to be an older building where our labs were, and my office was upstairs and the labs were downstairs, and this young Indian PhD student comes running upstairs. First of all, there's a big noise in the building, so something was happening downstairs, and Ramana, this Indian student, says, Dr. Harding, I think there's a problem in the centrifuge lab. Now, this is an example of understatement. Okay, I think there's a problem. So we came rushing downstairs. There was smoke everywhere, and this instrument wasn't this. It was an old MSc Centriscan. Was basically the drive had broken, and the force of the banging of the rotor against the side had dislodged the wheels on the centrifuge. So it was actually chasing people around the laboratory with this noise smoke. It wasn't funny, really. It was quite. It could have been quite dangerous. But we've had 2 accidents like that with the older instrumentation. It's because we've basically got second-hand equipment. Well, it's equipment that people had thrown out of the laboratories. That's how we set up our hydrodynamic centre. Yeah. Heaven knows why the government supported us as a national facility when we taught this. But it was before this was made in 1990. It wasn't possible to buy a commercial analytical centrifuge. It was only possible to get hold of older instruments that people had been throwing out, because in the 1970s and 80s, 1970s, coinciding when I did my PhD, there was a dramatic decline in interest in this sort of technology because people were using this stuff. We want to use high-resolution methods like NMR and crystallography for looking at structures and things. We don't want just shapes and things. And molecular weights, we can use electrophoresis and chromatography. That's and then people started to realise the limitations of electrophoresis. You have to bind SDS and all that sort of stuff to them. Chromatography, you had to make assumptions that the columns were not interacting with the materials, and you had to use standard markers, which were assumed to have the same conformation as your unknown. There was no SECMALs then, by the way. We don't need centrifugation. And then suddenly realised that the limitations of these other methods, and also the desire to understand information about interactions between molecules, and in an environment which is free of problems due to matrices, column materials which may not be inert, this is a free solution technique. So all of a sudden, people started to get interested in this sort of methodology again. So the first thing that happened is that we got a centre made at Nottingham because no one else was doing this type of experiment other than us. I think there was a couple of labs in Germany doing it, so people had to come to us until 1990 when Beckman had the idea of producing a new instrument which was compact, and so that's a bit of a history behind the Nottingham Science Museum and the Nottingham laundrette. Okay, it's slightly more sophisticated than the washing machine, I can guess it. Right, okay, gosh, that was all the introduction. Right, velocity sedimentation first of all. So that's what one of these cells look like. I should have brought one along, but you'll see that in the demonstration. So this sort of 4 centimetre long cylindrical construction. It has 2 channels, one for your solution and one for your reference solvent. So it's rather like a spectrophotometer, so you have to compare your signal going through your solution with that of a reference solvent. And if you look down on one of these centrifuge cells, of course this is spinning at high speed in the rotor with the centrifugal field in an outward direction. But if you look down on top of this, then after a period of time you'll see that you won't see, but the optical system will see material sedimenting. And this is your, say, protein solution or whatever it is. And you can see that there's a region of clear solvent that's left behind as the material moves towards the bottom of the cell. So as time progresses, this solvent solution boundary will move towards the bottom. And your optical system, as I said, needs to have a reference system as well. So this is the other sector has just clear solvent in. And you'll fill it right to the top. You leave a small air gap at the top of the cell. So there we are. It moves. It takes a few hours to go from there to there. So during that period, we can use, if it's a protein, we can use UV absorption optics. We can scan across the cell every 10 minutes, every half an hour, or whatever, depending on how fast things are moving. And we scan across the cell with UV optics at what wavelength? Protein, 280 nanometers. And there's a little blip here that corresponds to the solvent meniscus, because this signal is subtracted away from that signal. Okay, so this removes any background absorbance that might be present in the solvent. So by subtracting that signal away, you remove those background effects. So this is the meniscus in the solvent cell, which is a negative peak because it's subtracted away. This is the meniscus in the solution cell. Then you've got clear solvent here with no absorbance, and then a boundary depending on how far the protein has sedimented. And that will move progressively towards the bottom of the cell. So your optical system will detect how fast that is moving. And the rate of movement of the boundary, and apologies for this, but there should be a line underneath here which has got removed in the copy. So it's the rate of movement of the boundary divided, or per unit centrifugal field, divided by the centrifugal field. So rate of movement of the boundary per unit centrifugal field gives you the sedimentation coefficient. So you measure how fast it's going, divide by the centrifugal field, which depends on the rotor speed, and that gives you the sedimentation coefficient, which is a measure of the size and shape of your macromolecule. Symbol little s. And the units are Svedberg units, where 1 Svedberg equals 10 to the power minus 13 seconds. So 1 Svedberg is the same as 10 to the minus 13 seconds, not seconds to the minus 1, seconds. Okay. For the ABT Abbey students, in the self-assembly macromolecules book, which we've given you, or the one that's on the Moodle, this is incorrectly given as seconds to the minus 1. Okay, the unit is Svedbergs or seconds. 1 Svedberg is 10 to the minus 13 seconds. And what we also do, what was commonly do, is because the sedimentation coefficient will depend on what solvent you're using. You know, if it's like it's water or phosphate buffer or whatever, it'll go much faster than if it's going through a glycerol solution or syrupy solution. And because of the high viscosity, it will slow the sedimentation down. So what we do is we standardize to standard conditions. So we standardize the sedimentation coefficient using special formulae on computers to the density and viscosity of water at 20 degrees centigrade. So whenever we measure our sedimentation coefficient is from this technique, it's quite usual. So we can compare different sedimentation coefficients for different macromolecules to standardize or normalize our sedimentation coefficient to the viscosity and density of water at 20 degrees centigrade. And also, we have to correct for our old friend, what's that phenomena where macromolecules get in the way of each other and repel and all that sort of nonsense? Non-ideality. So we have to correct for non-ideality. And we do it one of two ways. We can work at very low concentration where non-ideality effects are small, or we can make measurements at different concentrations and extrapolate back to zero concentration. Right. We can also use refractive index or interference optics, it's called. We don't have to go into the details of this, but instead of getting this boundary, which we get with absorption optics, instead we get these stripy fringes. Okay, and each one of these lines is basically one of these lines. Okay, so we've got multiple concentration profiles here, and what the computer program does in the ultracentrifuge is it takes all this data and averages it out, does what's called a Fourier transform, and you get something like this. So the computer program converts that into one of these profiles for refractive index optics. So this we would use for proteins, nucleic acids. This we would use for any macromolecules, proteins, nucleic acids, and polysaccharides. Right, that's how we record our sedimentation velocity. Now this is our favourite milk protein. This is for the undergraduate guys. Beta lactoglobulin, our favourite milk protein, or my favourite milk protein. Yeah, probably mine, I think, yeah. Is there another milk protein? Anyone name another milk protein? Nutrition scientists, hands go right up. Yeah, I don't know. Any other milk proteins we know? Come on, that's casein. That's right, casein. Yeah, absolutely. Casein's a very interesting one, actually. So this is beta globulin at 25 degrees centigrade, 50,000 RPM. And the direction of sedimentation is this way, and we've scanned every 20 minutes. So this sedimenting boundary has been scanned every 20 minutes. So what happens is the computer will work out how fast this is moving. This is absorbance at 280 nanometers. And from the rate of sedimentation divided by the centrifugal field, it's worked out that the sedimentation coefficient is 2.97 plus or minus 0.03 Sedbergs. Okay, so it's obviously smaller than the 11S soya bean globulin, which actually is a multi-subunit protein. That's why this sediments faster. So 2.97 plus or minus 0.03 Sedbergs, which is a typical value for a globular protein. This is a dimeric protein, beta-lactoglobulin. That's what these patterns look like. Right, a little bit of theory. We have a break, and then we'll do equilibrium after the break. So, the sedimentation coefficient is the velocity divided by the sedimentation, how fast it's going, sedimentation rate, divided by the centrifugal field. And the centrifugal field is R, which is the distance from the center of rotation, times the angular velocity squared. And the angular velocity is just, when people see a Greek letter, they get frightened. Oh gosh, sigma, omega, oh dear. So omega, is just 2 pi divided by 60 times RPM. So you take your RPM value, so for that beta lactoglobulin experiment, the RPM value was, 50,000, yeah? So times 2 pi divided by 60 gives you the angular velocity, and the units are radians per second. Radian, what's that? How many degrees are there in a circle? 360. How many radians are there in a circle? 2 pi, that's right, yeah. 2 pi. That's where that comes from. So it converts minutes to seconds, and 1 revolution is 2 pi radians. Yeah, correct. So it's omega squared r. So that's how you get that. And in fact, the computer program does it for you anyway. So r distance center of the rotor. So here's some examples here. Lysozyme, S 1.91, this is 20 degrees in water, that's minus 13 seconds, or 1.91, how many Sedbergs? 1.91 Sedbergs, that's right. Bovine serum albumin, sedimentation coefficient in Sedbergs is 1 Sedberg is 10 to the minus 13 seconds, so the sedimentation coefficient in Sedberg units is 5.01, that's right, yes. Fibrinogen, so the elongated protein, higher molecular weight, 330,000, 7.9 Sedbergs. Yeah, must be a misprint on there, because what's missing? Avalmin, that's right, yes. So clearly a misprint. 3.4 Sedberg, 3.5 Avalmin. So that's an example of a sedimentation coefficient, depending on the sizes and the shapes of the macromolecules. Just a couple of points. It's related to molecular weight and shape by that. So S is a constant, which depends on things like R, the gas constant, temperature. V bar, what's V bar? V with a bar across it. The partial, specific, what are you trying to say? Volume, yeah? The volume per unit mass, yes. The density. So depends on the density of the solvent, density of the solute, and the temperature. And this, that's the molecular weight, about 2/3. That's for spheres. Okay, it's a different value for other types of macromolecules. F over F naught, this rascal here, is called the frictional ratio. Is the frictional ratio, and it's the friction coefficient of the macromolecule divided by the friction coefficient of a sphere of, I need a page to write this, sphere of the same mass and anhydrous volume. So the frictional coefficient of a macromolecule, the frictional ratio, F over F naught, is the friction coefficient of a macromolecule. I measure its frictional resistance, divided by the friction coefficient of a sphere, spherical blob, of the same mass and anhydrous volume. Okay, so this, what's the units of this frictional ratio? No units, that's right, because the units cancel out. And we find that the frictional ratio so this F over F naught, come on, pen, equals 1 for a spherical unhydrated protein or unhydrated macromolecule. So if you've got a spherical particle which has no hydration, no water attached to it, then you get a value of 1. Otherwise, it's greater than 1. So you get a value of 1 if it's spherical and unhydrated, otherwise it's bigger than 1. If it's less than 1, you made a mistake. Yeah? Okay. So that's the frictional ratio. It's a measure of shape of the molecule and hydration. And it's related to the actual ratio, relation long axis to the short axis. The constant depends on the solution density, viscosity, and protein density. You don't need to remember that formula. I'm not going to give it you anyway. S, for comparison purposes, is corrected to standard conditions. That is water, the viscosity and density of water at 20. It doesn't mean you're measuring water. you've got to have some ions in there to shield charge effects and reduce non-ideality, but we just convert it to standard condition afterwards. And we either work at very low concentration or make measurements at a series of concentrations and extrapolate back to zero concentration to get rid of non-ideality. Yeah? So you can see now I made that big fuss at the start of the course about non-ideality. It happens time and time again. With ABT navies, we saw that also in viscosity with the other module. So, yeah. Undergrads, we saw that with the osmotic pressure, non-ideality. Same again with sedimentation coefficient. You do all that, then you can make some interesting measurements or deductions about your protein solution, as we'll see in the video. Right, shall we just a 5-minute stretch legs, just a quick break, and then we'll have a full break at 11 o'clock before we have the demonstration. So if we reconvene back here at 5 minutes time? Yeah? Just time for a run around the block, and then back here, yeah? Stop raining now. Right, while we're in the break, Abbey students, Gleb on Friday. We've got
2 groups.
Either do 2 groups or we can combine everyone together. What do you think? Because there's 7 in total for Abbey. Should we do them all together?
Together.
There's enough room in the lab to do them all together.
Guys, for the wait a minute. About the next Friday, the groups we are talking about.
Do you need us for that?
No, your course rep will handle that for you.
Okay.
That's what he's paid for. Oops.
So I think it's are they doing viscosity?
Yeah, viscosity. We can maybe take a bit longer with the if we do get all 7.
I
and
think
then
2 groups is good because otherwise, if we guess them in one group like we did before, I mean, it's kind of takes. Yeah, I think we split them in 2 groups.
Okay, or we just do the 2 concentration groups, and they watch Thomas do the measurement. We could do the concentration separately, I suppose. No, or should we just
Do we
do
do
2 groups?
concentration as well?
Yeah, they do the concentration.
They already had the concentration on this spectrum.
Oh, the Abbey's always done that, haven't they?
Yeah.
Well, that's okay.
That's,
Yeah, you've already had the demonstration on with Gleb on using the spectrophotometer.
yeah.
In that case, we can just have 2. Yeah, we'll split 2 groups doing the viscosity. Yeah.
So 3 and 4 people. So just guys decide who wants to go first and who.
The question is, can we get them both done in the morning, or
We can.
just doing the viscosity?
I mean, I think it's up to you.
Yeah. Okay. So the first group comes in at 9. What time do we say?
9.
It's 9.
9:30. Let's do 9:30.
9:30. On the second group.
Oh, it's 9:30, 10:30, 11:30, 12.
12.
12:30. Because we need to
Cool the bath down.
Cool the bath down and probably
12:30.
1 o'clock.
1 o'clock. Yeah, 1 o'clock. And then we'll be done by
9:30 and 1 o'clock.
Okay.
And we'll be finished. The second group will be finished by 1:30. Okay, but Benito, who's doing what?
9:30, and then we'll be finishing about
12.
12.
They're just doing the viscosity, not the concentration. Yeah, 11:30 they'll finish.
11:30. And then the
Second
other
group,
guys
1 o'clock.
is 1 o'clock.
And we'll finish by the
By
dentist's
3.
favourite time, which is dentist's favourite time is.
Who?
What's the dentist's favourite time?
Dentist.
Dentist.
I think it's
No.
no,
Anyone know
it's
what the dentist's favourite time is? folks? Jay, what's the dentist's favourite time? No.
It's not the time, right?
The dentist's favourite time is 2:30.
That was close.
You know what's 2:30?
No.
2:30. No.
Right.
That was bad.
So we'll be finished by 2:30.
I need to remember it from a Christmas joke thing.
Yes, I think so.
So we start then at 10.
Do you know when we're coming back on?
10, yeah, 10 o'clock, yeah, 10 o'clock.
10. Do you know when we're
So
coming
we
back
go
on
at
Wednesday?
10 o'clock and we will finish about 11:30, but let's assume 12, right, is a maximum.
Yeah.
2 hours.
That's
And
fine.
here we will aim to finish
14:30.
2:30 and 3 p.m. maximum.
Yeah, okay. So we've got to split them into two groups then.
Or they can
Well, they, if you saw this, yeah, cross reference,
Yeah,
you
yeah,
can do
yeah.
that.
Other question: the dressing code for the symposium. The dressing code, like normal.
Dress
formal,
code
informal.
is, let's have a look.
Yours is perfect.
Okay, thank you.
It's
fine,
it's
actually,
business. It's
yeah.
kind of business casual. So because you're not presenting, if you would be presenting, like
That's
Steve
different.
gonna be in the tie.
Absolutely, a tie.
Yeah.
Yeah, always dress up. If you're not sure, always dress up. So we say sporty casual. Sporty casual.
Sporty casual. This is fine.
Business
This
casual.
is fine.
Yeah, as long as there's no holes in the jeans, let's have a look.
Yeah. Okay. No hold.
No, the baby is slightly smarter without acidic trainers next to it. It's like
I wouldn't wear trainers. That's sort of smart. Yeah, I wouldn't wear.
I
or
wear
dark
them
trainers.
once in 5 months, so it's a lucky
Yeah.
day.
Okay.
So look, you know, smart but not over smart.
No, that's okay. I mean, it's
You know
fine.
when you normally come back from this trip, like year to year?
We do come back, yes.
Well, that hopefully. But I mean, do you know what time?
We leave 5:30, so it depends
No.
on traffic.
Okay.
Oh,
So
5:30.
We leave 5:30,
Oh, you're gonna be 7 p.m. 5:30.
7:30.
About
Oh,
8.
so
8.
eight.
Yeah. I'll make an announcement at the end before the
Right.
break for the demonstrations. Okay, don't worry. Yeah. But key thing is getting there at 5:30 or 5 o'clock. 5:30.
But then you go to the lab.
Yeah. 11 o'clock.
No, to the lab in Cambridge after the conference.
Oh, lunchtime.
Oh, lunchtime.
Or if you get there early, if you do get there early, we might just show them. It's just 5-minute walk from Downing College. I'm going past my old obstacles. So it's a fabulous place. You can just go. All the expertise was there. Like we had this problem. I had this problem. I was thinking about it actually for trying to lips always. Trying to work it out. So just went to the maths department. And a guy called John Allison was there. And they were just falling over you, these guys. They were just looking for problems to solve. Oh, great. Let's help Steve. It's great. It was they're brilliant. You know, they're brilliant, and they knew it. It was a great experience.
Do we get an itinerary for Wednesday by any chance?
He's not going for looking. We'll give you an itinerary.
So we'll start at 5 in the
Starts off with
morning,
alarm clock.
and then 5:30 is the
Yeah,
way
we,
back.
yeah. But I'll make an announcement before we split for the demos and things at 11 o'clock. I'll make an announcement for the okay, guys, are you all back? Yes, 17. Okay, folks, so I haven't been thrilled by sedimentation velocity. What was the second method the second exciting method we can use using this technology? That's the one, yeah. So, this is a velocity experiment where we're looking at this, oh, hang on, what's happened here? This boundary, and it's sedimenting to the bottom of the cell. That's at high speeds. Okay, we get this sedimenting boundary, and the sedimentation rate per unit centrifugal field gives us the sedimentation coefficient, which depends on the size and the shape. which we can get from this exciting parameter called the... You couldn't see that, could you? Because that was in the way. Sorry about that. If I just lower that. Yeah. When you first started as a lecturer at university, you go through this lecture training course. Have you been on that? Do you have to go on this lecture training course at the main campus?
I did before in University of Queensland.
Okay, so you're an old hand anyway, but my training course was 1984, which is 35 years ago. So things like this in the way, and this standing in front of the screen, which we all talk about, you tend to forget about that after 35 years. So errors like that, I apologise for. Or not making sure you have pens that write clearly. Actually, you're normally the provider of pens, Glenn.
Unfortunately, my pens are in the...
Yeah. But you could all read that, could you? That was all right. Yeah, fine. Fine, so this is sedimentation velocity, high speed sedimentation rate divided by a centrifugal field gives you the sedimentation coefficient, measure the size and shape. Now, at lower speeds, what happens is that the forces of sedimentation and diffusion come to equilibrium. You don't get that, which is moving down with time, but you get a steady state situation where the sedimentation that way and diffusion forces that way balance each other out, and you end up with a concentration which is steady state. So we just started concentration distribution. So it doesn't change, it stops like that. With a low concentration at the meniscus, building up to a high concentration at the bottom of the cell. And then your computer on your centrifuge will detect this, and when it realizes it's not changing anymore, it's come to equilibrium. That's right. It'll tell you that, and then you can stop the run and you can analyze the data. And this time what we can do is this profile was measured by, well, absorption optics or refractive index optics, depending on what you've got. What you can do is you transform this plot of concentration against distance from the center of the rotation to a plot of log concentration against distance squared. And you don't need to know the theory, but if you've got a single monodisperse, you'll know what that means now, monodisperse solution of a well-behaved protein like of albumin, except it's a glycoprotein because it's got a bit of sugar, well-behaved protein like of albumin, single molecular weight, that's low concentration, so not too non-ideal, then we get a straight line. If you put log concentration, either log to base E or log to base 10, against distance squared. And the slope of that plot equals the molecular weight times a constant, which depends on the rotor speed, depends on the gas constant and all this, T, depends on, rubbed it off. And yeah, if I wasn't a professor, I'd get a job as a magician, because I'm very good at losing things and making things disappear. Yeah, actually, it's sort of seen it. And parameters like this. When you do the problem, you'll see where all this lot fits in. Believe me. So that constant depends on things like the specific volume, the rotor speed, the temperature, the density of the solvent, all this sort of stuff. If you know all that and measure the slope, we can get the molecular weight of your material, which is a weight average molecular weight. I'll say that, more about that in a minute. Right, so how do we record this? Right, we can use absorption optics first of all. Providing the absorbance is less than, well, I said 1.0 there, and that was a little bit pessimistic. In the lectures on spectrophotometry, I said that, what was the limit for the Lambert-Beer law absorbance? I said it was about 1.4. Yeah, but on ultracentrifuge, the optical system wasn't quite as developed as a spectrophotometer, so we would always sort of stay below 1.0. But now, with improvements, we can go to 1.2, 1.4. And Gleb, if you had a really expensive spectrophotometer, we said to the ABT group, we said we could go up to 1.5, didn't we?
Yeah.
As the limit. So, yeah, for most purposes, with the centrifuge, less than 1.2, 1.4 is the limit. And the absorbance is directly proportional to concentration. And if the absorbance is too high, then what we can do is repeat the experiment, but with a shorter cell, reducing the path length. Yeah. You can't always dilute the solution because then sometimes you want to see what's happening at higher concentrations, but we can use shorter path lengths. Or we can use the other optical system, which is the refractive index optics, if the absorbance is too high. Right, so we use absorption optics if it's a protein, and this ties in with our chromatograph. Here it is. Yeah, so it's easy to convert the equilibrium absorption scan into one of concentration versus distance from the rotor center. So we can use, if we know the extinction coefficient and path length, we can convert absorbances into concentrations. Or we don't have to convert at all. We can just work in concentration in absorbance units. You don't have to convert to grams per mil. And okay, this is because what we're measuring is the slope of a plot of concentration, logs to base E, against distance squared. Now the nutrition students, food science, have used logs to base E before. It's just the same as logs to base 10. Log to base EX is 2.303 log to base 10x.
303 log 10 base.
2.303 log to base 10x. So they're just the same as log to base 10, but you've got this factor of 2.303 in front. So don't be frightened of logs to base E. Look at that. Open the curtains and it's... Can you see that all right? Yeah. I think there's one of them missing. Right, so the molecular weight is d log C dl squared. What that means is d log E, C dr squared is the slope of a plot of log concentration against distance squared. That's what that is there. And the constant is 2 R, the gas constant, T, temperature, the gas constant in CGS units, which we give you, and divided by 1 minus V bar. For a protein, it's about 0.73. For proteins on Earth, yeah. ABTs don't understand that comment, not yet anyway. But Abbeys and undergrads do, yes. So 0.73, 0.74, and rho is the density of the solvent. Okay, which is about 1 normally. And omega squared is the angular velocity squared. Yep. Well, omega is 2 pi over 60 times RPM. So log CR squared, MB. Note that d log C dr squared is the same as d log absorbance dr squared. Yeah, well, why? Why is that? Well, the reason is that the reason is D, oh, it's flipping pen. D log there's no pen on the side there, is there, Glenn? Or actually another option. Success. Nice. So, D, a little maths lesson, folks. There might be a factor of 2 somewhere in there, but d log y with log e is the same as 1 over y dy dx. Don't ask me to prove that, okay? So the thing is that the units of y here cancel. So it doesn't matter if that, say, let's do the same thing for the d log EC d r squared equals 1 over r squared dc dr. So it should be squared.
1 over r.
1 over r dc dr. Yeah, that's it. Sorry, that's.
And rc. 1 rc.
We have a correction here.
Like that. dc over dr.
Right. You sure the r should be there?
Yeah, because the r dr equals dr square. And
That's right. Yeah, no, that is right.
And 1 over 2 here.
Yeah, that's correct. Yeah, so that means, yeah, Okay, so the point is that the units of concentration cancel. So it doesn't matter if your concentration units are in grams per mil, kilograms per mil, kilograms per meter cubed, absorption units, interference units, refractive index units, or whatever. The units of concentration cancel, but not the units of R squared. R squared there, you've got R times R here, which is R squared. So the units of R squared are preserved. So what are the units of the slope of that plot? Units are, if the distance is measured in centimetres, the units of the slope of that plot is are
Centimeter square? Is it centimeter square?
almost. It's on the bottom. So it's, if it's divided by, therefore it's centimetres to the minus 2. Yeah, that's right. So the unit is centimetre to the minus 2. Yeah, let's write that more clearly. Minus 2. I think it's the board actually. Don't mean that pen was working beautifully through there. So the unit of the slope is centimetres to the minus 2. So it doesn't matter what the concentration units are. We don't have to convert from absorbance units to gram per mil. We don't need to know what the extinction coefficient is. It's that easy. All right? Clear? What will make that really clear? If you did a question on that. Yeah, and we'll see that in a second. Right, now, as far as interference optics is concerned, okay, here's what we're looking down on the cell again, and we've got our solution in this column, and we've got our solvent in this column, our solution in this column. Notice, I said before, we don't fill the cells, and when we did the velocity experiment, oh, come on, velocity, there we are. See how we almost fill the cells, but not quite. With equilibrium, it's the same thing, but we don't put as much in. We only put a small amount in of solution and solvent. And the reason for that is that by having what's called a small amount of liquid in the centrifuge cell, it gets to equilibrium much faster. So the sedimentation and diffusion forces get to equilibrium much faster. And if we didn't do that, then we'd be waiting all week for the forces to get to equilibrium if we had a whole cell full. So we just fill the reference cell and the solution cell just between 0.07 and 0.2 mils, depending on the optical path length of the ultracentrifuge cell. And by keeping the column short, you can get to equilibrium a lot faster. So for small peptides, oligosaccharides, it could take a few hours.
But for larger glycans, polysaccharides, lipobacines, mucin, proteins, it can take over 3 days. And if stability is a risk, then it's worthwhile running the instrument at a lower temperature, say a few degrees centigrade, rather than the standard 20 or 25 degrees centigrade. Right, now these flat fringes here correspond to a comparison of light going through the air part of the solution channel compared to the air part of the solvent channel. So it's air against air, so that's why you get these flat lines. But then these curved fringes correspond to solution compared to solvent. And so in the solution cell, you've got a low concentration at the solution meniscus, building up to a high concentration at the cell base. Of course, the solvent has no macromolecule. And each of these fringe profiles reproduces a plot of concentration in the solution channel relative to distance from the meniscus, which is position A here, and B is the cell base. And the fringe displacement in the vertical direction, after allowance for any biomolecule concentration left at the meniscus, here we call this the meniscus concentration. So the fringe displacement in the vertical direction after this allowance will be directly proportional to the concentration C in the solution, C measured in mg per mil or gram per mil or whatever. So the same equation applies as if we were using absorption optics. By the way, these short columns apply to whether you use interference or absorption optics for a sedimentation equilibrium experiment. Same equation applies. So this time, with interference optics, the concentration expressed in terms of fringe displacement units as opposed to absorbance units. And it's d log e, the natural logarithm, d log e c d r squared, where r is the radial displacement from the center of the rotor. Times a constant, again, the same constant as before, which depends on the rotor speed, the partial silic volume, temperature, and the density of the solvent. And the molecular weight is given by the slope of plot of log concentration against distance squared times the constant. And if you've got a heterogeneous polydispersed system, as you often get with large glycans, then the average slope will give you, this will be curved, and the average slope will give you the average molecular weight or molar mass, which will be a weight average molecular weight, as opposed to osmotic pressure you saw in the other module, BIOS 4074, which gives a number average molecular weight if you've got a heterogeneous or polydispersed system. And again, using the same arguments we discussed before with the absorption optics, you don't have to convert fringe concentrations to absolute concentrations in grams per mil, because the units of concentration cancel when you consider the the logarithm, the differential term in the logarithm. Okay, there's one final thing to be aware of when measuring molecular weights by sedimentation equilibrium in the analytical ultracentrifuge. Values for the molecular weight or molar mass so obtained at a finite concentration are only apparent values, which we note by this subscript A here, because of non-ideality, thermodynamic non-ideality, which we met in BIOS 4074 when we were just talking about osmotic pressure, but it also applies to sedimentation equilibrium, applies to light scattering, diffusion, and hydrodynamic non-ideality with viscosity. Because of the much bigger size of macromolecules compared to solvent molecules, and for any unsuppressed charge behavior. Although in practice for proteins, particularly small proteins, then the apparent molecular weight, molar mass, is approximately equal to the true molecular weight, molar mass, especially for concentrations less than about 1 meg per mil. But for larger glycans, like conjugates, polysaccharides, nuisance and things, an extrapolation to zero concentration may be necessary. So with osmotic pressure determinations and molar mass, molecular weight, if you've got non-ideality as a problem, then just take measurements of a series of concentrations and extrapolate back to zero concentration when these non-ideal effects tend to zero. In the case of sedimentation equilibrium, you plot the reciprocal of the molecular weight. Don't forget this will be a weight average against concentration, and this is the equation you fit. At this time, unlike with osmotic pressure, where you had 1 plus B times the concentration, this time it's 2B. Same osmotic pressure, thermodynamic second virial coefficient, which we met in the other module. For many purposes, if you work at very low concentration, provided you get a sufficient signal, then this concentration goes to zero. This term will go to zero, and the apparent molar mass, molecular weight equals the real molecular weight, molar mass. Okay, right. There is a question based on all this, and this is your coursework correct question, and it's called Analytical Centrifugation of a glycan. And the first part A is explaining the difference between sedimentation velocity and sedimentation equilibrium. And it asks you about 200 words, describe these differences, and maybe a couple of diagrams. And then part B, what are the two optical systems we use on an analytical ultracentrifuge? And then part C, there's a calculation based on an FC fragment of an antibody molecule, which is a glycan. It's got a carbohydrate attached. And it says here that this FC fragment was examined by a researcher using sedimentation equilibrium. In the ultracentrifuge, in phosphate buffered saline, pH 6.8, ion 10.1, at a loading concentration of 1 mg per mil. So possibly within the limits of thermodynamic ideality. So a concentration correction or non-ideality correction is not necessary. The experiment at 20 degrees centigrade was observed using the interference optical system. And when the patterns measured, the following results were recorded for the concentration C as a function of distance from the center of rotor. Complete the table below. So distance from center of rotor is R. And CR is the concentration expressed in fringe displacement units. Got 4 data points here: distance, concentration. And the first thing you've got to do is complete the table. So you square the distances, and then you work out what the natural log is. And on your calculators, if you have them, or on the calculator function on your laptop or mobile phone, it's log EC is the same as LNC, natural logarithm. So don't use log to base 10, use log to base E, natural logarithm. So you do that, then you plot log to base C of CR, the y-axis, versus distance squared on the x-axis. And then you evaluate the slope of d log CR dr squared. And what are the units? Don't forget you got an r squared on the bottom here, dr squared. So don't forget to consider the units of distance or distance squared. And then having worked out the slope and given the units, then you're given these constants. The buffer had a density rho naught to 1.0021. The partial split volume V bar is 0.746 mil per gram. The operating speed is this, which corresponds to an angular velocity omega of 2137 radians per second. So we've done the conversion of revs per minute to angular velocity in radians per second for you. Otherwise, you would have used the 2 pi divided by 60 times the RPM to get the angular velocity in radians per second. Then, from the slope of the graph, and using the formula below, this one here, what do you estimate for the molecular weight or molar mass of the FC fragment? In giving your answer, pay attention to significant figures. So if you look at this table here, the data is correct to between 2 and 3 significant figures. So take that into account when expressing your final answer. So a sensible number of significant figures. Okay, so it tests your understanding of one of the important techniques we've been talking about, analytical ultracentrifuge, and just tests how you represent data. You can plot this yourself manually on graph paper, or you can plot it using Excel. But be careful with the settings on the Excel, because sometimes it truncates the significant figures when working out a slope. So make sure you have enough significant figures on the setting for the Excel. Okay, let's see what you get.